Welcome to Networks Professionals.
Ever wonder how an AI goes from knowing absolutely nothing to making predictions that actually shape our world? Well, today we're opening up the playbook. We're going to break down step by step how machines really learn, and we'll make the whole process from start to finish super simple. Let's jump in.
We throw around the term machine learning all the time, but what's actually happening under the hood? Is it just studying a digital textbook? Over the next few minutes, we're going to crack that question wide open. And you'll see, it's not some kind of weird magic. It's a logical and, honestly, a fascinating process.
When you boil it all down, AI is really about one thing: taking a bunch of raw information, data, and using it to make smarter decisions or predictions. That's it. That's the core mission we're going to unpack today. So, here it is, our playbook. A pretty simple four-step process. First, we have to explore the data we're working with. Then, we need to pick a specific task we want the AI to solve. After that, it's time for the training montage, where the real learning happens. And finally, we give our model a big final exam to see if it actually learned anything.
Okay, step one, and honestly, this might be the most critical step of them all. Before you can even think about teaching a machine, you have to become an expert on the textbook you're giving it. And that means getting to know your data inside and out.
In the world of AI, this is called EDA, or Exploratory Data Analysis. The best way to think about this is to picture yourself as a detective. You're just sifting through all the evidence. You're looking for patterns, for clues, or for anything that just looks a little off. This initial detective work is what stops huge problems from popping up later.
But what if your data isn't just a simple textbook? What if it's a whole library with thousands or even millions of different data points? Well, that's where a really cool technique like PCA, or Principal Component Analysis, comes in handy. It's like a master summarizer. It boils down all that complexity to its most essential parts. It helps find the real signal in all the noise, which makes the data so much easier for a model to learn from.
Okay, so we understand our data now, we've explored it. The next step is a huge choice. What question are we actually trying to answer? In the world of machine learning, this usually boils down to one of two fundamental missions.
So our mission is either going to be a regression task or a classification task. Basically, are we trying to predict a specific number, like a price, or are we trying to sort something into a category, like saying this is spam or this is not spam? Let's break those two down.
A regression task is all about the numbers game. You're trying to predict a specific number. The key here is continuous, meaning it can be pretty much any value in a range. Think about forecasting the weather, or estimating what a house is worth based on its size and location, or predicting next quarter's sales. These are all classic regression problems.
Now, classification isn't about numbers. It's about sorting things into buckets. You're just assigning a label. Your email does this 1,000 times a day, labeling messages as spam or not spam. Figuring out what type of flower is in a photo, or diagnosing a medical scan. Yep, those are also perfect examples of classification.
And now for the main event, the training process. This is the learning part of machine learning. And it's not some single flash of insight. Oh no, it's a relentless loop of trial and error, and just getting a little bit better each time. This is the training montage of our story.
The biggest challenge during training is what's called the Goldilocks problem. If a model is too complex, it overfits, which is like a student who just memorizes the answers to the practice test but can't answer any new questions. If it's too simple, it underfits, meaning it didn't really learn the material at all. The goal is always to find that just right model in the middle.
So, how does the model even know if it's getting better? Well, it has a digital teacher called a loss function. After every single guess the model makes, the loss function calculates exactly how wrong it was. It basically says, hey, you are off by this much. Go back and try again. That loss function spits out just one single number, an error score. And the entire training process becomes a game. The goal of the game is to automatically tweak the model over and over again to get that error score as close to zero as humanly, or I guess mathematically, possible. All right, the model has trained. Its error score on all the practice data is super low. But is it actually smart? Does it really get it? Well, it's time for the final exam, where we test it on data it has never ever seen before.
You know, a single test isn't really good enough. A much stronger method uses a technique called cross-validation. All this means is you split the data up into a bunch of different sections and you test the model on multiple combinations. It's like giving a student 5 different versions of the final exam to make sure they really know the material and didn't just get lucky.
So after all that testing, we need a final grade, right? A single number that just tells us how well it did. And for that, we often use something called the F1 score. You can really just think of it as the model's final report card.
So, the F1 score is a bit smarter than just a simple accuracy percentage. It cleverly balances 2 really important things. The first is precision, which asks, of all the emails we said were spam, how many actually were? The second is recall, which asks, of all the actual spam emails out there, how many did we manage to catch? By balancing these two, the F1 score gives us a much more reliable grade on its performance.
And that's the playbook. Just like that, we took a pile of messy, raw data, we played detective with it, we gave it a clear mission, trained a model through that loop of trial and error, and finally, we graded it with a tough exam. We have officially transformed pure information into a powerful predictive tool.
So now that you know the fundamental steps, from digging into the data to training to testing, the real question is, what would you do with this? Whether it's forecasting sales or identifying diseases, or maybe something nobody's even thought of yet. The playbook is yours now. So what problem would you solve?
Thanks for watching.